Okay, so how does a lens design program compute relative illumination? I'm gonna go through this video very quickly, like super fast. So if you want to follow the mathematics, just click pause. All right, this is relative illumination, and it's given by the ratio of these two quantities. So what this is, if you're familiar with radiometry, irradiance is proportional to something called projected solid angle. And since relative illumination is a ratio of irradiances off axis to on axis, I can just take the ratios of projected solid angle. All right. And so this is given by the ratio of these sums here and sine squared of these angles here. What these angles are the angles of rays that you trace coming out from the exit pupil, surrounding the exit pupil. That's why it's called circumferential rays or just rim rays. Any number of them. And if the exit pupil is not circular, like some arbitrary shape, then you can still take the root mean square average. And this is something that I talked about in a previous video. All right. So this is my approach to computation using rays. And I'm going to show you how, in a moment, how it leads to how it's done in a lens design program. Right. So if you take the ratio of these, cancel the pi's, cancel the 1 over n's, you get this form of the formula here. Okay. So what is theta prime? Theta prime, by the way, is the chief ray angle in image space. All right. So how do we know it's right? Okay. So uh, as usual, how do we know something is right? We take limits. In the limit that the exit pupil, if you look at the exit pupil sideways, I mean, if you look at the exit pupil to the image plane, like sideways in a layout, look at these quantities here and assume that the exit pupil is very small compared to the distance z prime and r prime, then the ratio simplifies to this, and assuming you take just 4 rays about the exit pupil, like top, down, left, and right, then it simplifies to this, then it simplifies to this. What I have here is a ratio of a prime to a naught prime. That is the exit pupil area off axis divided by exit pupil area on axis. You get areas because the top here looks like an area, right? Pi times some radius squared plus pi times some other radius squared divided by 2. That's like an average, right? So some kind of area, and this area is orthogonal to this line here, so it's a projected area from the image plane times cosine theta prime. So you times cosine theta prime twice, you get a cos squared theta prime here, and then a prime is just an area associated with that plane. And then you've got z prime and r prime, so that ratio is cosine theta prime squared times cosine squared theta prime, so you get cosine 4 theta prime. So this here is the image space formulation of relative illumination in a limit of low aperture, which I showed in the previous video. In fact, to recap, that's this guy right over here. Okay, remember you can compute relative illumination in image space or in object space. Okay, so that's not all. Now, remember that the sine of an angle is equal to the cosine of the of 90 degrees minus the angle, right? So if you write in terms of cosine, and you look at these variables here, then you can express relative illumination in terms of cosines, and you get a direction cosine space. All right. If you project these quantities to this plane here, you can trace out an approximate ellipse if you choose 4 rays again, top, down, bottom, and left, bottom and top, down, left and right. Okay. And so if you trace out this approximate ellipse and do some algebra, you end up with a formula that looks very much like, in fact, it is Matthew Rimmer's formula. If you're familiar with Rimmer's work, it's excellent work in lens design. In 1986, he wrote a paper called Relative Illumination Calculations, in which he derived this formula a slightly different way from which I derived it, but it's the same thing. And this is used in Zemax, and I'm not sure if it's used in other programs. Rimmer worked for, I think, in a company that developed Code 5, so maybe it's done in Code 5. I don't know, you tell me, right? But this is how it's done in Zemax, and this is how I arrive at this equation. And that's all I want to share. Thanks for your time. Bye-bye.